Today's topic is continuous symmetries. And what's a symmetry? I gave you 3 definitions for discrete groups, but it turns out that most definitions I gave you while we discussed discrete groups also work for continuous groups. So almost everything except we'll have a notion of Lie algebra, which is specific to continuous group, but almost everything that I told you works. So one of the way to say it is if I start someplace in a state space, so I have my state space, M, and I start at some point x, and then I rotate that point, g of x. So what the group does, group action does, it takes something in the space and move it to someplace else without destroying it, just changing its position. So that's, the famous active transformation. G puts us into point gx. So that's where we are. Then we apply our dynamics, our law of nature. So we say ft. So now we start at this point, and ft does, one of these amazing things that dynamics does. And time t later, we are at a point here, x prime. And now what the invariance means is that this is the same as if I started here. So I just went ft of initial point, then rotate. So it's the same as though I started at x, I went time t later, and then I did a rotation. So that says that symmetry operation when system is symmetric and dynamics commute. And that's very useful because they commute for any time. So we can do it instantaneously for small steps, we can do it for big steps. It's a very powerful statement. So you can either rotate, do the thing, or you can do the thing and rotate and you'll end up at the same point. The same point you can write in several ways, but it's, for example, g of f of t of initial point, or you can write it at f of t of g of x. So that's global statement of invariance. Now, when we have continuous time flow, so this applies equally well for discrete time dynamical systems and continuous systems. Discrete ones go through a set of points rather than trace out a curve, but the statement is the same. But when we have a continuous dynamics, we can also just say what happens to my dynamical vector. Because at this point I have equation of motion that said x dot at this point is the vector field, which is time invariant vector field. The local statement in time, but global in group. And toward the end of the lecture I'll do them both local, but global in group says that you just take an infinitesimal step in time. It's totally simple, and I'll write it in the other version of the formalism. It says that if I start at x, I rotate it, and I evaluate the velocity field. So it's this velocity field here. And then I go back. I get the velocity field here. Now remember, our equations of motion is that they're all written in first order form. So it says the variable are changing is this vector field. So this is a statement that physicists like. They say that I can also use this notation G minus 1 more abstractly dot V dot G, meaning as a set of function I first apply rotation, then I apply velocity, then I go back, and the law of motion is invariant. So that is symmetry. It's a set of group of elements that either commute with a finite time evolution or they preserve the law of motion under coordinate changes that are representations of this group. And then we say that our dynamics, which was M, state space F, law of evolution, is G equivariant. Applied mathematicians like to say this. I'm perfectly happy if you just call it invariant. That's what physicists do. The distinction is explained in the book.